Chemical equilibrium and Le-Chatelier's principle. Imagine going to a mall and trying to walk up the escalator. If you are slower than the escalator, you are going to fall down. You can definitely move up if you are faster than the escalator. And if you match your rate exactly to the rate of the escalator, you are going to be stuck. You are in a state of dynamic equilibrium. Such a dynamic equilibrium is also established in reversible chemical reactions. A reversible chemical reaction is one in which the reactants are getting converted into the products, while the products are also simultaneously getting converted into the reactant. Let us take a reversible reaction A giving me B. Let us say that initially at time t equal to 0, we had 10 molar of A and say no B was formed, so we had 0 molar of B. Now this A is getting converted to B at some specific rate, right? Let us call this rate forward, while B is also getting converted to A, let us say at rate backward. In our example, let us say that A is getting converted to B at say 6 molar per minute, and because we do not have any B formed as of yet, so there is no rate backward. So after 1 minute, the concentration of A will drop down to 4 molar, right? Because 6 molar of it has reacted, while the concentration of B will be 6 molar because A and B are in 1:1 ratio. Now, since the concentration of A has decreased from 10 molar to 4 molar, thus the rate forward is also going to change. It is not going to be 6 molar per minute anymore. In fact, from law of mass action, we know that rate is equal to some constant into concentration of the reactant raised to its stoichiometric coefficient. In other words, in our example, the rate forward will be equal to some constant, let us say K forward, into concentration of the reactant raised to its stoichiometric coefficient. So we have a stoichiometric coefficient 1 out here, so raised to the power 1. Similarly, for the backward reaction, the rate is going to be equal to some constant, let us say Kb, into concentration of the reactant. If you're looking at the reaction B going to A, the reactant is going to be B raised to its stoichiometric coefficient, which is going to be 1. Simply put, we can say that as concentration of A increases, the rate increases, and if the concentration of A decreases, the rate decreases. Let us now come back to our example. Since the concentration of A has decreased from 10 molar to 4 molar, the rate forward is going to decrease, right? Let us say that the rate forward decreases to say 3 molar per minute. And now because there is some B formed, we are going to have a rate backward, say 1 molar per minute. So when we go into the second minute, we can see that 3 molar of A has converted into B, but 1 molar of B has also converted back into A, right? Now this reaction is in 1:1 ratio, so we can say that 3 mole of A has reacted, but 1 molar of A has formed. So effectively 2 molar of A is getting reacted, and thus concentration of A will now drop to 2 molar, while concentration of B is going to increase to 8 molar, right? So the concentration of A has further decreased, and thus the rate forward is going to decrease further still, and let us say that this decreases to 2 molar per minute. Now the concentration of B has increased, right? So rate backward is going to increase, and let us say that this also increases to 2 molar per minute. In such a scenario, in the third minute, we can see that 2 molar of A is getting reacted, but 2 molar of A is also getting formed. So effectively the concentration of A is going to remain 2 molar, while that of B is going to remain 8 molar, right? So because the concentration of A has not changed, and let us say that we are carrying out this reaction at a constant temperature, so because the concentration of A has not changed, thus rate forward is going to remain 2 molar per minute, and similarly rate backward is also going to remain 2 molar per minute, right? Now the reaction is still going on, but since the rate forward is equal to rate backward, so the concentrations do not change, and we can say that the system has achieved a state of dynamic equilibrium. Let us now see how an equilibrium reacts if we try to disturb it. Let us take a reversible reaction A giving me B, and let us say that it is at equilibrium. Now, if I try to disturb this equilibrium by adding more A, in fact, if I add 1 molar A at equilibrium, at that instant, the concentration of A increases to 3 molar, right? While concentration of B still remains 8 molar. Now, because the concentration of A has increased, so rate forward is also going to increase. It's not going to be 2 molar per minute anymore. Let us say that rate forward is 2.5 molar per minute. So the instant I add more A, the concentration of A increases, and as such rate forward increases, but the concentration of B still remains the same, so rate backward still remains 2 molar per minute. Now clearly this system is not at equilibrium because rate forward is greater than rate backward. So now in the next minute the concentration of A is going to decrease and it becomes 2.5 molar, while concentration of B increases to become 8.5 molar. Rate forward now further changes, and let us say rate forward now becomes 2.4 molar per minute. Rate backward would now increase since the concentration of B has increased, and let us say rate backward becomes 2.1 molar per minute. Now in the next minute, concentration of A will become 2.2 molar, right? Because 2.4 molar of A is getting reacted, but 2.1 molar is also getting formed, so effectively 0.3 molar is getting reacted, while that of B will become 8.8 molar. Rate forward will now also change accordingly, and since the concentration of A has further decreased, rate forward will further decrease, and let us say it becomes 2.25 molar per minute. Similarly, rate backward is going to increase from 2.1 molar since concentration of B has increased, and let us say that it also stands at 2.25 molar per minute. Thus we can see that rate forward again becomes equal to rate backward, and thus a new equilibrium is established out here. In short, if we disturb the equilibrium by increasing the concentration of A from 2 molar to 3 molar, then rate forward becomes greater than rate backward, and so the reaction moves in the forward direction, and in this process concentration of A decreases until a new equilibrium is achieved at 2.2 molar. Now we can also look back at this and say that if we disturb the equilibrium by increasing the concentration of A, the system actually does not like it and it wants to go back to the original position, and that's why in this case the concentration of A needs to decrease, and thus the reaction needs to move forward. Similarly, if we disturb the equilibrium by say increasing the concentration of B, then in this scenario rate backward would become greater than rate forward, and therefore the reaction would move in the backward direction till a new equilibrium is established. In other words, we can say that if we disturb the equilibrium by increasing the concentration of B from 8 molar to 9 molar, the system does not like this and it wants to revert back to the original status quo. So in this case concentration of B needs to be decreased, so the reaction keeps moving backwards until it reaches a new equilibrium. This is actually the Le-Chatelier's principle, which states that when a system in equilibrium is disturbed, it shifts in that direction in which the disturbance is negated, or we can say nullified or decreased, until a new equilibrium is established. We are now going to randomly disturb our equilibria and use Le-Chatelier's principle to predict the direction in which the reaction moves. Say we disturb the equilibrium by decreasing the concentration of A from 2 molar to say 1 molar. The equilibrium has been disturbed, and according to Le-Chatelier's principle, it will want to go towards the original state. So concentration of A needs to increase, and this can be achieved if the reaction moves towards the left. In other words, if we decrease the concentration of A at equilibrium, according to Le-Chatelier's principle, concentration of A should increase, so the reaction move towards the left. Obviously, this makes perfect sense because as concentration of A is decreased, rate forward now becomes lesser than rate backward, and because rate backward is more, so the reaction starts moving in the backward direction. Similarly, if we disturb the equilibrium by decreasing the concentration of B from 8 molar to say 7 molar, so again the system will want to go towards the original equilibrium. So in this case, concentration of B needs to increase, and this is achieved when the system starts moving to the right. Simply put, if we decrease the concentration of B, then concentration of B needs to increase, and therefore the reaction needs to move to the right. This too makes sense because if the concentration of B is decreased at equilibrium, that means rate backward is decreased and it will become lower than rate forward, and so the reaction is going to move in the forward direction. We can now simply play along and say that if we have disturbed the equilibrium by increasing the concentration of A, then concentration of A needs to be decreased, and this can be achieved if the reaction moves in the forward direction. And similarly, if we increase the concentration of B, concentration of B needs to be decreased, and this can be achieved if the reaction moves in the backward direction. Thus, instead of actually diving down and thinking about the rate forwards and the rate backwards, we can use Le-Chatelier principle as a rule of thumb to predict how the system is going to behave when an equilibrium is disturbed.